Hey folks, welcome to this episode on resonance structures. So by now you've seen how to draw our Lewis structures using our mathematical method. And if you were trying to attempt to do something like nitrate NO3 minus, you could have compared with someone else and saw that you might have gotten a slightly different structure in terms of where the double bond is placed. Now, with some structures, you can't represent that structure with just one Lewis structure. The reason why is the double bond or the multiple bonds can move locations. And what we call these electrons that actually can move, because remember that these bonds are just made up of electrons, is that they are called delocalized electrons, meaning they're not really associated with a single atom or a single bond. When we look at ozone, for example, here we can see one structure of ozone where you have the double bond on this side between these two oxygen atoms. And when we look at this one, the double bond has actually switched places. It's not like the molecule is flipping around. It could, but in this case, we're saying that if we label this oxygen number 1, this will also be oxygen number 1. So the molecule is not actually flipping around. It's the double bond that is moving, and that's because the electrons that are associated in this bond are actually going to be flipping onto the other side, and again, we call them delocalized electrons. So when we see something like this, we actually use something called a resonance structure. These are called resonance structures because they are one and the same. They are the same molecule except for the difference in the double bond. Now, both of these structures are equally as stable, but there are going to be some instances where you can have a number of different structures in terms of where the multiple bond is, but one will be more favorable or more stable than the others. So when we look at here's our example of nitrate. So remember that's going to be NO3 minus. And if you did your Lewis structures, you would see that you could either have the double bond up here, the double bond over here, and the double bond over here. Now also know that you also have an overall negative charge, which is shown in the brackets over here. But what you can see is that in each case, all of these molecules can actually exist. Double bond here, here, here. So these are all resonance structures. Now, again, you're going to be seeing that one is going to be more favorable than the other. In this case, all of them are actually equally as favorable. But again, in some instances, one will be more. And we'll show you how to do that in a couple moments. Now, when we look at these resonance structures, and here's a carbonate, CO3 2 minus, and you can see that one of the oxygens has a minus 1 charge, and this one has a minus 1 charge. I'll show you what that means in a second. But in this case, the actual value or the actual structure of carbonate is actually a combination of these three, because you won't actually see it as only one of these in existence. What will happen in this molecule is that the double bond will actually move to the different bonds. And eventually you'll kind of get like a hybridized version of it where you actually see this kind of, the double bond would be here, 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 the next second here, and then here, and then here, and here, and then here, and then here, and here. So eventually what you're going to start seeing is you're going to have this kind of bond where the double bond is shared between all the individual bonds over here. And we call this a resonance hybrid. Now, one of the more popular ones that we're going to be exploring this year in terms of molecules is benzene. And benzene is an aromatic compound, so it has this kind of 6-carbon structure that has a double bond, double bond, double bond. And just like other resonance structures, you'll see that the double bond can actually switch places. So this double bond will move over here to get over here, that double bond will move over here, etc., etc. And it'll keep moving around and around. And the reason for this is that these double bonds are actually made up of things called the p orbitals. And the electrons exist in these p orbitals, and they can keep moving around. So what you actually see is if the electrons keep moving around from one side to another, they actually start forming, they start going like this, like this, like this, like this. Same thing at the bottom over here, at the lobes on the bottom. And you kind of get these donut shapes above the actual structure. And this is why these resonance structures for benzene are actually represented in this kind of structure where you actually see the carbons and a circle in the center showing that these double bonds are not belonging to any two carbons. They're actually belonging to the whole structure, and they keep moving around and they eventually form a circle just like that. Now, I was telling you about that you can find out if a structure is more stable than another using something called formal charges. And what this actually shows is how many electrons are actually owned by each atom. Now we use this equation over here to help us figure out the formal charge of each atom in the structure. So what you're actually going to be doing is you'll find the formal charge for this atom, and this atom. Now if the whole molecule has a overall charge, for example nitrate had NO3 minus, then the formal charges actually have to add up to that negative charge. So some of them might be plus, some of them might be minus, but the sum should equal up to the negative charge. Now here, for carbon dioxide, we actually don't see any overall charge. So that means that the atoms that make up this molecule should all add up to 0. Now that means they could be 0, or they could be, for example, -1 and +1. Overall, that would be 0, and this would be 0. So you have to add up your formal charges to the overall charge of the molecule. So let's go ahead and look at this equation. So this equation tells us the number of valence electrons. So if I was to look at oxygen, the number of valence electrons from the periodic table, it's in group 6, so it's going to have 6 valence electrons. Now, the second part is minus the number of covalent bonds. Now, you might see this different ways. You might see this half of the number of electrons in a covalent bond, but I'm just going to use the number of covalent bonds here. So the number of covalent bonds that oxygen has is 1, 2. So that's 6 minus 2. And the final part of this is minus the number of electrons in lone pairs. So it's not the lone pairs themselves, it's the number of electrons. So here I have a lone pair, and here I have a lone pair. I have 1, 2, 3, 4 electrons. So it's going to be minus 4. So 6 minus 2 minus 4 is going to give me 0. So same thing for carbon. Carbon has 4 valence electrons. It's engaged in 1, 2, 3, 4 bonds. So minus 4. And right now in this arrangement, you actually don't see any lone pairs above or below. So it's going to be minus 0. So 4 minus 4 minus 0 will give me 0. And if we look at this last carbon, again, we have 6 valence electrons. It's engaged in 2 bonds, minus 2. And finally, we have 4 valence electrons, so 4. So 6 minus 2 minus 4 is, again, 0. So here, as you can see, the sum of all these is going to be equal to 0, which is the overall charge of the molecule. Now, these formal charges also give us a hint as to which one is the most stable structure. So in this case, what I'd like you to do is do the formal charges for each of these molecules, aka do the formal charge for each of the atoms in the molecules, and make sure that the overall sum equals up to the overall charge of each molecule. So do the formal charges for this, and for this, and when you're done, come back, we'll give you the answers, and we'll talk more about which one is a little bit more stable and which one is more favorable. Okay, so go ahead, pause the video now. Okay, so welcome back. Here are our formal charges. So you can see in the first molecule over here, we do get our sum to equal -1. This is going to be 0, 0, and -1. Here as well, here's -2, and then we add 1 to get -1. And then here we just have a -1. So what we want to do is we want to try to figure out which one is the most favorable in terms of stability of these three molecules. And usually it's the ones that have the least formal charges that add up to the molecule's charge, in this case -1. So here, the least favorable actually is this one over here, because you can see that we have two actual formal charges above 0. Whereas here we have 2 zeros, here we have 2 zeros. So this one is our least favorable. So we can cross that one out. Now, it's a competition between this one over here and this one over here. Now, which one is it going to be? Next slide. So it's actually going to be this one over here. The reason for that is because they have the same formal charges, what we have to look at next is where is that negative charge located? In this case, it's located on the sulfur, and the sulfur has an electronegativity of 2.5. While in this case, the negative is landed on the nitrogen, which has an electronegativity of 3.0. So when we look at this, we want to have that negative charge on the most electronegative atom. Remember what electronegativity means. It's the ability to pull a negative charge to it, aka electrons. So in this case, it will be more stable with that atom that wants to have that negative charge. And in this case, the nitrogen beats out the sulfur, and therefore this is going to be our most stable and most favorable structure. So thank you so much for watching. See you soon.